assume. Degrees Kelvin just becomes uppercase K, and mole becomes MOL. All very good, useful abbreviations, although I don't know, that mole abbreviation doesn't exactly save us gallons of ink. They found that they did need a unit for electric current, and it's something called the ampere. And this one has always personally surprised me. They found that they did need a unit for how bright a light was, what they called luminous intensity. It happens to be called the candela. Now, of the 7 base units, you will probably encounter the first 5 in your chemistry class: meters, kilograms, seconds, kelvins, and moles. 6, if your course includes a unit on electrochemistry, the ampere. I don't know of any chemistry course that discusses candelas. Well, the idea now is that starting with these 7 fundamental units, all other units must be derived from them. Well, this leads to some interesting things. For example, suppose I said to you, what would be the correct SI unit for volume, the amount of space taken up by an object? Students will typically say, oh, I know that. We talked about that in the last lecture, the cubic centimeter. Au contraire, no. Now, you may like cubic centimeters. I like cubic centimeters. We will be using cubic centimeters throughout this entire course. But it is not the official derived SI unit of volume, because the whole philosophy of this system is that the 7 base units establish the system, and all other units must be derived from these 7 base units. So what would be the correct SI derived unit for volume? Well, volume is distance cubed. Therefore, if I follow this philosophy, the correct unit of volume has to be the fundamental unit of length, the meter, cubed. That's a big volume. A cubic meter would be a box 1 meter by 1 meter by 1 meter. Now, this is a pretty large volume. Aren't you glad that your lab equipment doesn't consist of beakers with volumes of cubic meters? Most people just assume that all scientists completely embrace the metric system. But in fact, there are many critics. And one common criticism is that many of the derived units are not of convenient size. And the cubic meter is certainly one of them. Of course, you can argue that just because the standard unit of volume is the cubic meter, that doesn't imply that you have to have large beakers in a lab. Just label them correctly. Okay. But that would mean that a beaker that is now so nicely labeled as being 250 milliliters would instead have to be labeled 0.00025 cubic meters. Now, which label do you like better? Well, because of this difficulty, what I call the inconvenient size of some of the units, you will still see a lot of what might be called practical units being retained. Included among these are things like milliliter, liter, gram, degrees Celsius, even millimeter of mercury, and many others. The committee actually decreed that certain of these units could be retained for a limited amount of time. To me, it actually appears that they are going to remain around for a very long time. Indeed, one could make an argument that the number of additional units that are being used every day may actually be growing, not shrinking. Once you understand the basic philosophy that every other unit has to be derived from the 7 base units, you now can run through several different kinds of units. For example, we've already discussed the cubic meter, the fundamental unit of volume, a cube, 1 meter on a side. We might ask, well, what would be the SI unit for area? Well, for simplicity, we might assume a square. Then area is a meter times a meter, or square meter. What would be the SI unit for the speed of an object? Now, that isn't trivial. If I asked you how to tell me how fast something was moving, you might say miles per hour if you lived in the United States, or perhaps kilometers per hour if you lived in Canada, for example. But if we use SI, It has to be the fundamental unit of length, the meter, divided by the fundamental unit of time, the second, or meters per second. When you take a physics class, and it's not important at this time that you understand what these terms mean, you'll discuss something called acceleration. How fast the speed of an object is changing. The number of meters per second the speed of an object is changing per second. So the SI unit comes out to be meters per second squared. It can get pretty involved. In physics, you'll talk about force. You'll learn that force equals mass times acceleration. Mass is measured in kilograms, acceleration in meters per second squared. So force turns out to be measured in units of kilogram meters per second squared. They give this unit a name, a Newton, and a symbol, uppercase N. When you get to energy, we'll talk about energy in chemistry. In physics, you learn that energy is force times distance. So it's newtons, which is the unit of force, times meters, which is the unit of distance. Since a newton is a kilogram meter per second squared, and we have to multiply it by another meter, you come up with units that truly begin to lose meaning. The unit of energy is a kilogram meter squared per second squared. Now, perhaps you can come to some intuitive meaning for this, but I think for most of us, that's pretty difficult. But we'll give it a name, the joule, named after a scientist named Prescott Joule. We always seem to feel better when we give something a name, and we'll give it a symbol, uppercase J. Now, you are not expected to understand all of these units that we just mentioned, but you should understand the philosophy that all other units must be derived from the 7 base units. So let's see if we've understood that. Take a few moments, stop the video if necessary, and try to answer this question. What would be the correct SI unit for density? Well, if you thought or yelled out, hey, I know that, we just talked about that in the last lecture, grams per cubic centimeter, that's what we used in the problems. Sorry. Intelligent, sensible answer, but not correct. Grams per cubic centimeter is a wonderful unit for density. That's the unit for density that we're going to use in this course. But it's not the SI unit, because the SI unit for density must be derived in terms of the 7 base units. Well, density is mass per volume. How much mass is contained in 1 unit of volume? Since the base unit for mass is kilograms, and the base unit for volume is the cubic meter, then the SI unit for density has to be kilograms per cubic meter. Now you might ask, why didn't you use that in the density lecture? Because no one is using kilograms per cubic meter, at least not around here. At one time, believe it or not, I was using a textbook that was actually published in Canada. And it did use kilograms per cubic meter, and that really was kind of inconvenient to me and my students. And I'll tell you why. In the last lecture, we talked about an object having a density of 3.45 grams per cubic centimeter. And we imagined holding a little cube in the palm of our hand, and we imagined 1 little cubic centimeter, and we imagined 3.45 grams. I think that was pretty easy to imagine. If you want to talk about this density in kilograms per cubic meter, it comes out to be 3,450 kilograms per cubic meter. Okay, we can probably imagine a cube 1 meter on a side, but can you really get a feeling for a mass of 3,450 kilograms? I mean, that's like over 7,000 pounds. I doubt it. Kilograms per cubic meter, while perfectly defined, is not a very convenient unit to come to grips with. And that's one reason why we tend to retain so many additional units. They are of convenient size for what we're talking about. Now, the SI system, just like the previous version, still has what are called prefixes. There are quite a few of them, I believe 20. If you are currently enrolled in chemistry, your teacher may or may not require you to memorize some or perhaps all of them. In my view, there are more prefixes than most students really need to know from memory, although several of them are encountered so often, it probably would be a good idea to just know them rather than having to refer back to a chart of something all the time. I suspect you will learn many of them rather quickly, for no other reason than the fact that you will be seeing them used so often in problems. Going through the prefixes is kind of a fun intellectual exercise, so let's run through them once. What I mean by a prefix is the following. Suppose you have a base unit. Take whatever you want. Well, don't take the kilogram. Let's say it's a meter. That's 1 of whatever it is. Now, 1 is equal to 10 to the 0 power. Be sure to remember that. Occasionally, a student will think 1 is 10 to the first power, but 10 to the first power is 10, not 1. So 0 becomes the exponent of the base unit. So what if you had a large number of something? Well, then we put a prefix in front of the symbol for the thing telling us how large it is. Here are the prefixes that are often used when you have large numbers of whatever you are talking about. I've highlighted the ones that I personally think are the most useful for you to know. The largest defined prefix is 10 to the 24th. It's called yotta and given the symbol y. I don't know why they didn't call it lotta. I thought that would have been the greatest name for the biggest prefix. I got a lot of meters, but they called it yotta. 10 to the 21st is called a zetta, capital Z. 10 to the 18th, an exa, capital E. 10 to the 15th, peta, capital P. 10 to the 12th, tera, capital T. 10 to the 9th, we call it giga. That actually isn't the correct pronunciation, but everybody calls it giga, so we will call it giga. You know, gigahertz on a computer, capital G. 10 to the 6th is a mega, capital M. 10 to the 3rd is kilo, and here they use a lowercase k. 10 to the 2nd, hecto, lowercase h. And 10 to the 1st, deca, which has a 2-letter symbol, the only one, dA. You notice that we do not have prefixes for every power of 10. For example, we do not have a prefix for 10 to the 4th, although at one time such a prefix actually did exist. We also don't have prefixes for 10 to the 5th or 10 to the 7th, or many other possibilities. There really isn't much of a need for them, and you're probably glad since it means there's going to be fewer to learn. There are prefixes for 10 to the 1st, 2nd, and 3rd, and after that they jump by powers of 3. If you have less than one of your base unit, if you have a fraction of your base unit, the prefixes are the following. 10 to the minus 1 is called a deci, symbol is lowercase d. 10 to the minus 2nd, centi, c. 10 to the minus 3rd, milli, m. 10 to the minus 6 micro. They actually use a Greek letter mu here. 10 to the minus 9th, nano, lowercase n. 10 to the minus 12th, pico, p. 10 to the minus 15th, femto, f. 10 to the minus 18th, atto, a. 10 to the minus 21st, zepto, z. And 10 to the minus 24th, iacto, y. If you ever heard of the Marx Brothers, somehow the last 2 prefixes remind me of Chico, Harpo, Zeppo, and Iacto. Now you may think that this is a rather complete introduction to the metric or SI system of measurement. Hardly. I am completely serious when I say that it would be quite possible to devote this entire series of lectures, all 36, to the history of measurement and the SI system. There are literally several dozen different defined quantities, along with all kinds of exceptions and qualifications, etc. If your teacher ever asks you to prepare some kind of a extra report, maybe for extra credit or something, this could provide you with an excellent topic. Now, one of the most common tasks required in many high school chemistry courses is the ability to convert from one unit to another, both within the metric system and between the metric system and the English system of measurements. In the next lecture, we will take a look at various ways in which this can be done.